It only skipped like 2 seconds. It's going now.
Do you have enough battery?
It says it has enough battery, so it's got like an hour and 20 minutes left.
Okay. All right.
Okay.
Because if that died, I'm going, I'm so screwed. Okay. So, anyway, as we do these acceleration equations, here's the dumbest thing that you can do, is read a problem and immediately go, ooh, what equation am I going to use? No. Bad things are going to happen. You are never going to thoroughly understand the complexity of these problems if the first thing you try and do is pick an equation. Won't work. Okay? It will not work. So, let's talk about this equation. And you're going, I've never seen this equation before in my life. Yes, you have. So, let's talk. Let's say that you have a velocity time graph that starts up here at, say, 10 meters per second, and it comes down here like this, and let's say that that's 5 seconds. Okay? So, Rosie, could you find the slope of that line? And if this is the velocity time graph, what would that slope represent? Acceleration. Now, how would you find the slope of that line? First off, is it going to be positive or negative? Negative. Okay? And how would you find the slope of that line?
Say rise over run, but
I would say rise over run, or change in y over change in x. So, what are the two coordinates for this point?
0, 10.
Okay, so that's at 0 and 10, and this point out here is at 5 and 0, right? True? So, what would you subtract?
The y and the x.
So maybe 0 minus 10 over 5 minus 0? Now, is the 10 meters per second my initial velocity or my final velocity?
Oh, initial.
Initial.
Yeah.
Now, so would the 10 meters per second be my V naught or my V? Yes. V naught is always the initial, okay? A naught, acceleration naught, force naught, whatever. Anytime you see that 0, remember that is always going to be the initial. So here's the deal. If you don't know this equation, which let's pretend that you don't, and I just gave you this graph, you would sit here and go, oh, okay, this isn't a problem. I'm going to take 0 minus 10, right, meters per second, over 5 seconds, and you would get negative 2 meters per second squared, which would represent what? Acceleration. Right? And which would be the slope of the line. True? Now, if you use this equation, right, and go, oh, acceleration is final velocity minus initial velocity over time. So in this case, if you just said, well, I like equations. Well, cool. We happen to have one just for this. So this would be 0, oddly enough, minus 10 meters per second over 5 seconds. And oddly enough, you would get the exact same answer. So when you look at this equation of acceleration is change in velocity over time, or v minus v naught over time, all you're finding is the acceleration of the object, which is the same as the exact same slope as the line on a velocity time graph. Okay? So if you remember, oh, acceleration is just the slope of the line. Boom, you're done. That's all you have to worry about. Now, if you look at this, v equals at plus v naught. Now, if you think this through, okay, yes, I said the t word. If you think this through, all this is a y equals mx plus b equation. And you're going, no, can't be. These aren't like numbers, they're variables. Yes, but it's the exact same thing. Look, this is your y-intercept, right? Which in this case is going to be, this is actually, so this here, right? This is going to be where you're going to start. This is your slope. Time is graphed on the x-axis. And v naught is what? Your y-intercept. So in this case, what's my y-intercept? 10 meters per second. Guess what? That's my initial velocity. This is going to tell you what my velocity is over some period of time, right? And this is just my acceleration. So if I take this equation, y equals mx plus b, right? and rearrange it, I get acceleration. So these two equations are identical. All they are is written in a slightly different form. Okay? Got it? Good? Fantastic. Now, I'm going to clean this up just a little bit. I'm going to redraw. So I got 10 meters per second. I'm over here at 5 seconds, and we're coming down like this, right? And that's 0, and this is the velocity time graph. Now, Braden, could I find this area?
Yes.
Yes, and what would that area get me? Displacement. So how could I find that area? It looks surprisingly like a right triangle, and how do you find the area of a triangle?
The base times height.
Yeah, 1/2 base times height, right? So the area of any triangle is 1/2 base times height. True? Now, in this case, what is the height of the base going to be? But what is it going to represent? The initial velocity, right? So in this case, the base is going to be some velocity. True? Excuse me, the height is going to be some velocity. The height is going to be some velocity. The base is going to be time. And hopefully we don't struggle with 1/2 and everybody knows what that is. Okay? Now, the area is going to be the same as what? My displacement. So that's going to be my displacement. So what I could do is I could write this as x equals 1/2 time times a velocity. Now, when I multiply meters per second times seconds, I get what? Meters, which is what displacement is going to be measured in. So in this case, if I wanted to calculate my displacement, I could take 10 times 5 and get 50. Take half of that, I'd get 25. So in this case, that area would be 25 meters. Good so far? Beautiful. Okay. Now, keep all of this in mind. So, what you're going to do in this lab, now, get up, we need to spin this thing over, is that you're going to work with, put this down here, might be easier to see, these ramps, okay? And they're pretty cool because they're pretty low friction, and they actually have a meter stick basically glued on the side of them that goes from 0 up to 122 centimeters, okay? So what you're going to do is you're going to take this and put it on one end on a 2x4. So you've got an inclined plane, pretty shallow, okay, pretty shallow inclined plane. And here's going to be the short version of the lab. You're going to take a cart, okay, and you're going to give it a push so that it goes up. Oh! Try it again. So it goes up, stops, comes back down. So maybe a little bit farther. Okay? Now, let's talk about what the cart does. Now, just like before, there's a couple of things we're not going to include. Listen to me. We are not going to include the push. Okay? So we're going to start the analysis at the very instant that you let go of it. That's where it starts. And then we're going to stop the analysis when it gets back to that exact same point. But we're not going to include the stop. So don't include the push. Don't include the stop. So it's like we're going bink. And it's going to go, and then it's going to come back. Now, what do you observe? What are some things that you observe about the motion? Danny, what's one thing that you observe about the motion?
It changes direction.
It changes direction, which means it has to do what three things, Danny?
Slow down, stop, and speed up.
Does it do that? Yeah, okay, right. So it slows down on the way up, stops. Classic idea, comes back down. Now, what's causing it to do that?
The incline of the
This is true, but there's something else that's important that we need. Now, let me ask you this, and this would be cool if I had this. Every physics teacher in the world would be jealous. But let's say I've got a switch that I can turn off the gravitational field inside the room. Okay? So imagine I could turn off gravity inside the room. Okay? It would be the ultimate physics room to have. Okay? But let's say that I could shut off gravity. And I gave this thing a push. What would it do?
Just keep going.
What?
So there's no, gravity's not pulling it down.
Yeah. If I shut off the gravity switch and give this thing a push, it's just going to go and just take off in a straight line, which would be cool to see. Okay? But I don't have a gravity switch. I've put in for it, and they haven't installed it yet. So the other thing that's going to make this happen is gravity. Now, do you think gravity is a fairly constant force? Yeah. It isn't like we have to wake up in the morning and check our phone and go, ooh, what's the gravity forecast for the day? You know, gravity is pretty much a fixed value. Or it would be cool if you had some variation, like, ooh, gravity's not going to be very strong today. Maybe I can finally dunk. Okay? Or gravity's going to be really, really strong today. Oh, I'm not going to play golf. All right? So gravity's pretty much a fixed value, and that's a good thing. That's one less thing that we have to worry about. I don't have to worry about waking up in the morning and going, oh, yep, okay, gravity's still there. We're good. Okay? So gravity's a fixed value, and that's a good thing. So Galileo was actually one of the first ones to begin to study motion, and he used inclined planes, mainly because of the fact that it basically slows down the effects of gravity. Because if I just throw this thing up in the air, okay, the change in velocity is very, very rapid, okay, and it's hard to get good measurements. But if I give this a push, it's almost like being, oh, that was a good one. It's almost like being on the moon because of the fact that it slows this acceleration down. Now, so here's the data that you're going to need, okay? You're going to need a couple of things. You're going to need someone to push this thing, and you're going to need at least 2 people in your group to time the entire trip, okay? Now, I don't want to do this like the CART lab where it hit the wall. Okay? Where you had somebody timing up and somebody timing it down. I want 2 people to time the entire trip. And you're going to start it as soon as it leaves, and then you're going to stop it when it gets back to the exact same point. Okay? So, let's say that it leaves at 0.22 meters. You're going to stop that thing when it gets back to 0.22 meters. So you're going to need the entire time. Okay? The other thing that you're going to need is that you have to record the initial position of the cart, okay, where it is when the person that goes lets go of it. Not where they start to push, but where it is when it leaves their hand. Then you need somebody recording where it goes on its highest point, and then when it gets back to that point. Okay? So you need this position where it goes, and then as far as it goes up here. Now, you have to make sure that everybody in your group is going off the same point. Are you going to record the measurements off the cart that's closer to the bottom, or are you going to go off the end that's up here? Okay? That's what you have to decide. Because otherwise you're going to be off by the length of the cart. It really doesn't make any difference. Everybody just has to be on the same point. So you're going to go, dink, entire time, dink. Okay? That's all the data that you need. Now, you also need to take a protractor and record this angle. Okay? So somebody have their protractor handy. I'll show you the trick, the easiest way to record.
Oh, I guess, yeah.
Okay, so here's the easiest way to record this. Is because of the fact that it's like elevated, is take your protractor and put it on your cart, and then slide this thing until the bottom edge of the ramp is like lined up at wherever you lined up the center of your protractor. So slide that along until the bottom edge hits there, and then look on this edge and then record that degree. Okay? So, because you can't put it down here like this and try and measure the angle. Okay? It won't work. It has to be up here. So, and the cart just provides a nice little rolling surface go, boom. It's probably going to be probably something around 3 degrees. Okay? Not very much. So that's all the data that you need. The entire time, okay? The initial position on the way up, the final position on the way up. Now, here's another thing that we're going to start to do, and we're going to do this a lot, is that we're basically going to break this trip up into 2 halves. We're going to look at what's going to happen on the way up, and then we're going to look at what's going to happen on the way down. So even though it's one entire trip, we're going to look at this thing in 2 separate halves. Okay? Now, the other thing, so that everybody's on the same set of systems, we're going to make the bottom of the ramp the reference point. That's going to be 0. So you're actually not going to start at the reference point. You're going to start a little bit away from the reference point. Okay? Now, I suppose you could start back here and like give it a flick where, you push it from the bottom, but it's probably going to be something fairly close to 0, but not exactly 0. Now, you're going to have positive positions going up. You're going to have positive positions coming back down, okay? Because we're never going to go past the reference point. Don't do this and then like, oh, I'm just going to let it roll all the way back. Don't do that, okay? Stop it when it gets back to that point. So, on the way up, you're going to start with maybe an initial position of 0.12 meters. You might end up at 1.12 meters. Now, then on the way down, you're going to go from 1.12 meters back to 0.12 meters. So you're going to look at 2 different trips, basically. What's happening on the way up and what's happening on the way down. Now, Courtney, on the way up, what's my final velocity? Nope. Nope. So I'm going to give this thing a push. On the way up, at that point right there. Why? Why? Beyond the fact that I'm holding it. But if I'm not holding it, why does that velocity go to 0? So on the way up, and this is going to be important, on the way up, my final velocity is going to be 0. Now, on the way down, Paige, what's my initial velocity? No. Guess again. I'm going to give it a push. When that thing starts to roll down, what's the velocity that it has when it starts to roll down? I'm going to let go of this. What's the initial velocity on the way down? 0. Okay? So this is going to be important. On the way up, you start with a positive velocity and you end up with at 0, right? On the way down, you start at
0.
and you end up with a negative velocity, right? So we're going to go from positive to 0 to negative. Is it going to accelerate? Yes. Do you think we're ever going to have constant velocity? No. Okay? So it's always going to accelerate and we're never going to have constant velocity. Now, well, here's what you got going. There's the ramp. Just going to start some value here. It's going to go up, and then it's going to come back down. So, is the velocity going to change? Elijah, is the velocity going to change? Yes. In what way? Is it going to get bigger, smaller, change direction, all of the above? So it'll never get smaller or bigger? Yes, it will. All of the above. Now, on the way up, it's going to start with some positive velocity. True? Now, if I could shut off gravity, what would happen to that vector? It would stay the exact same all the way, and the cart would take off and it would go like this. Okay? Should be cool to see. It's not going to happen. Now, as it goes up, Abby, what's going to happen to the size of that vector? Is it going to get bigger or is it going to get smaller? Because it's going to be slowing down as it goes up, right? True? So, over the period of time, this vector is going to get smaller and smaller and smaller, right? Now, on the way down, what's it going to do? Then it's going to change direction, and it's going to get bigger and bigger and bigger, right? So, when something's accelerating, you're changing this velocity vector, and you're going to do it one of three ways. Either the velocity vector is going to get bigger, the velocity vector is going to get smaller, or the velocity vector is going to change direction. Okay, if any of those three happen, you're accelerating. And in this case, we kind of have all three. We're making it smaller, the velocity vector is going to change direction, and then it's going to get bigger. So we have all three things happen. Now, one of the things you're going to do is you're going to sketch a position time graph. So, your position time graph, okay, here's 0. I'll give you three options for your position time graph. Option A, option B, and then option C. So, A is the outer curve, B is the triangle shape, and then C is the kind of point one. So this is for the cart being pushed, rolling up, coming back down. So how many vote A? Okay. What about B? What about C? Okay. Now, Abby, what does the slope of a position time graph give you? Velocity. So, I wish you were right. Okay, and here's why I wish you were right, because C would be the coolest one to see, okay, to observe. Because if C is right, that I would push the cart, it would start off very slowly, and then it would speed up as it goes up the ramp, okay? And then it would start back down really, really fast, and then it would slow down right before it got to my hand. C would be cool, okay? If C was our world, it would be a lot more fun, okay? But it's not. Now, why can't it be B? Yeah, if B was right, it would be a constant velocity, okay? Which would be kind of cool to watch too, because it would go up at a constant velocity, not slowing down, and then it would stop all of a sudden, and then it would come back down at a constant velocity. So, B would be kind of cool to watch, but not as cool as C. Now, why is A right? It shows it starting with a high velocity and then slowing down, going to, and then speeding up. So, this is, and you're going to know the times. So, let's say that you timed it, and let's say that your total time was 2.20 seconds. Okay, that's your total amount of time. So if your total amount of time is 2.2 seconds, okay, how long is it going to take to get to the top? 1.1. Now, this is going to be important. As long as a path is symmetrical, whether it's something being pushed up the ramp, whether it's this thing throwing up in the air, as long as something returns back to the exact same point, okay, you can assume that the time up is the same as the time down. If it returns back to the same point, and that's a huge caveat, okay? If it returns back and it's symmetrical, which in this case it is. Now, we also need to draw the velocity time graph. I'll give you three curves on that. First off, where's my velocity time graph going to start? Is it going to start at 0? Reed, you shake your head no. Why?
Because we don't start the graph until we're done pushing.
Bingo. We don't include the push. If we did include the push, it would start at 0, but we don't include the push. So here's my velocity time graph. I'll give you three options on the velocity time graph. There's A, okay? Whoop. And then here's B, boring. And then you have C. Okay, so it's like Mick Jagger's lips. Okay, so you have A, then you have boring B, and then you have C, which is kind of the flip of A. So how many vote A? 1, 2. The Reeds vote A. What about B? Smattering of Bs. About 4 Bs, kind of all in the back. What about C? Okay, most of them, it's kind of a split. It's interesting. Okay? It's kind of a split. Hum. Now, let's talk. Slope of this line gives you what? Acceleration. Right? So, if this thing, let's talk about the reed line, okay? Which we're going to call A, right? The reed line. So, according to what you guys have, initially, you have a very big acceleration, right? And then the acceleration becomes less. And then when it starts to back down, you have a small acceleration. And then as it gets closer to the bottom, the acceleration becomes faster. That's what that line is saying. Now, the red line is saying that the acceleration is kind of slow at the beginning, and then the acceleration becomes greater as it approaches the top, and then it starts with a very big acceleration on the way back down, and then the acceleration becomes more gradual once you hit close to the bottom. Okay? Now, boring B just says what? That you had the same acceleration the entire time. So how can we resolve the situation?
What happens at the end?
That's how we resolve the situation. Rosie,
Yes.
what's this?
I just applauded myself.
Why?
Because the force never changes.
Why?
Because there's, the gravity's a constant.
Yeah.
The acceleration's going to be the same.
Ah. Are we going to change the mass of the cart? No. We're not going to drop an elephant on it halfway up. Okay?
Down the road.
The mass is going to remain constant. No changing the mass of the cart. Okay, that's a rule. They're my carts, you don't get to change the mass of them. So the mass is going to remain constant. What's creating the force to make it slow down or speed up? Gravity is, right? We just established early on that gravity is the same all the time. Gravity isn't going to fluctuate. Okay? It's going to be the same. So if I have the same mass with the same force, guess what? I have to have the same acceleration, which leaves you boring B. Now, you want the red or the blue line to be it. In your heart of hearts, this is intuitive to you because you're going, Mr. Burkamp, it slows down, it speeds up. Come on. This is like the Nike swoosh thing, okay? It swooshes, right? You all want to swoosh because, imagine that Nike, instead of the swoosh, Nike had this. Boring, okay? Marketing nightmare. Oh, it's the Nike line. Okay? No. You all associate speed with curves and all this good stuff. But you have to remember, what is acceleration? At the end of the day, what is the definition of acceleration? The rate at which what changes? The rate at which your velocity changes. Acceleration is not how fast you are going. Okay? And you all want to associate, well, it's slowing down and it's speeding up and it's doing all these cool things, it's changing direction. Yes, it is. Okay? But the rate at which that changes is the same because the force is the same. Okay? Got it? Wonderful. Now, we're going to clean this up. Here's my velocity time graph. And this is one of the things that you're going to do. And this is going to flip you out. Okay, I'm going to tell you this from according to your velocity time graph is going to look like this. But you're not going to know what the initial velocity is. Okay, you're not. Then you go, oh, Mr. Rickham, we have to draw a line and we don't know what the initial velocity is. Oh, dear Lord, we can't do this. Yes, you can. Okay? Now, let's say the entire trip is 2.20 seconds. Where is that car at that point right there? Sydney. 1.10 seconds. But physically, where is it on the ramp?
Oh, it's up there at the top.
Why?
Because it's, the velocity is 0 and starting to change.
Beautiful. Okay? So this is when my velocity is at 0. This is when I'm at the top, right? Wonderful. So this point out here is going to be 2.20 seconds. Does this show the criteria for something to change direction? Right. Does this show the 3 criteria for something to change direction?
Yeah.
Why?
Because it slows down.
Up to what point? Okay, so it's slowing down up to this point.
Yeah.
Yes? The velocity goes to,
Yeah.
it changes direction, and it
Goes back.
speeds back up, right?
Yeah.
Okay, so this matches all 3 criteria. You're slowing down, stops, speeds up. Now, this would be cool if the line did this. Why would that be cool to watch? Yeah, it would stop at the top and then speed up in the same direction. Like you kick in the rocket boosters and the warp drive, okay? And off it goes, which would be cool. Highly dangerous, but this would be cool, okay? But that's not what we have. So we just have the boring blue line, but it's effective. Now, at this point, you're going, I don't know what the initial velocity is, Mr. Burkamp. Oh, what am I going to do? Funny you should ask. What is this area in here going to represent? Displacement. Oh, all right. On the way up, are you going to know the initial position of the cart? Yes, you're going to know where it starts. You're going to know on the way up. You're going to know X naught. What else are you going to know?
Fine.
You know the final position. If you know the final position and the initial position, what can you calculate? By doing what? Final X minus X naught, right? Which is going to give me my displacement. Now, how is that displacement going to relate to this graph? Mr. Moon,
The area.
you know the area of this. Now, somebody, I think Graber, said the area of a triangle was 1/2 base times height. True? Are you going to know the area of this triangle? Yes, because you're going to know the final and the initial position of the cart. So you're going to know the area. You're going to know this. Are you going to know the base? Yes, because you're going to know how long it took to make the trip up. Now, what's the height going to represent? The initial velocity. Okay? So you're going to work backwards to calculate the initial velocity of the cart. And you're going, oh. Okay? Now, one of the things you will hear me say again and again and again and again and again and again and again. Do not put in the numbers and then solve the equation. If you're a freshman in an algebra class, fine. Okay? You're running with the big dogs now. Solve the equation first. So we need to solve that equation for h, which is the most jacked up h I've ever driven in my drawn in my entire life. Okay?
Yeah.
We need to solve for h. So, Elijah, how can I get h by itself? What's the first thing I want to do, keeping in mind that I hate fractions and freshmen? By doing what? By? 2. So this becomes 2A equals BH, right? Then what? Divide by my B, okay? So the height, which is going to be my velocity, is going to be 2 times my area divided by my base. Now, let's play the units game, okay? Let's play the units game. Cindy, what's that area going to be measured in?
Meters?
Why?
Because we're going to
Right? And the area is going to representing my displacement. Now, at this point, again, I have to undo 12 years of education. You've always been taught, area is always in something meters squared. No, in this case, area is going to be measured in meters, because it's my displacement. Now, the height of this, or the base of this triangle is even weirder. What's the base of the triangle going to be measured in? Seconds. If I divide meters by seconds, I get velocity, which is going to this is what that's going to represent. Okay? Now, Rosie, we okay?
I did not say velocity.
What did you say?
Nothing.
Shall we just never speak of it again?
Yes.
Okay, all right. We will never, I don't know what you said, but we will never speak of it again. Now, at this point, here's the ultimate big picture that you're trying to find. You're trying to find the slope of this line. You're trying to find the acceleration. On the way up, or at this point, will you know the initial velocity on the way up? Yes, because you're going to know the height of this triangle. When it reaches the top, are you going to know the final velocity? Yes? Are you going to know the time? You can find the slope of this line. Now, here's then guess what? Then you're going to find the slope of the line there. Now, here's the whole reason I wrote this lab. Okay? And this lab is like 2 pages long. Here's the whole reason I wrote this lab, and this is why I did this acceleration lab first, before we do the equations, is that you all get the idea, and it is ingrained in your head, and it makes sense that if I have positive velocity, negative acceleration means that I slow down. I do not fight that fight. You all get this. Here's what I fight, is that when this thing changes direction and starts to roll back down, you all want to flip the sign of acceleration and make it positive because it's speeding up. So I'm forcing you to analyze this motion first on the way up, which is going to fit within your framework, and that's going to be cool. You are going to feel uncomfortable on the way down because you want to flip the acceleration. Okay? Don't. All right? I'm just telling you, don't. Now, stop that while I hand that lab. Okay, so on the lab, here's the data that you need. The angle, okay? Measure that probably around 3 or 4 degrees. Total time, time up, time down, okay? And if you have 2 people time, you can kind of take the average. And now, if there's a big discrepancy, somebody screwed up, run the trial again. So, up the inclined plane, you're going to need the initial position of the cart. Make a decision. Are you going off the back of the cart or the front of the cart? Somebody observe where the cart is when it leaves your hand. Final position of the cart on the way up. Make sure that you record these in meters. Do not work in centimeters. This thing is laid off in centimeters, but you all are brilliant people and you can divide by 100 and move the decimal place 2 places to the left. Okay? I have faith in you. You can do this. Now, on the way down, you're going to have the initial position of the cart. What's the initial position of the cart going to be on the way down relative to the final position of the cart on the way up? It's going to be the exact same. So you're going to look at this. It's going to start at the bottom. It's going to roll up. And then it's going to start there, and it's going to roll back down. You're going to calculate displacement. How are you going to calculate that displacement? What minus what? Final minus initial. Okay? Boom, there you go. In terms of data, that is all the data that you need. Right there. That is all the data that you need. Now, there's some things I want to clarify. How are you going to use the angle? Over on page 2, okay, question number 21, says calculate the theoretical acceleration of the cart by using the following formula. A equals negative 9.8 meters per second squared times the sine of the angle. Okay? When we get down with forces, you will see where this equation came from. for now, just accept it as faith, okay? In about 2 weeks, you'll see, oh, okay, well, that all makes sense. So what this gives you is a theoretical acceleration if there is no friction on an inclined plane. So you're going to take negative 9.8 meters per second squared times the sine of whatever angle that you have. Let's say your angle is 3 degrees. So you can take the sine of 3 degrees and you're going to multiply it by negative 9.8 meters per second squared. That's all you have to do. It's just, this is going to give you a theoretical acceleration. Now, on the top of page 3, you have question number 22. Question number 22 says calculate the experimental error in the acceleration of the car by using your answer to number 19 as the experimental value and your answer to 21 as the theoretical. So when you do question number 22, if you don't remember how to calculate experimental error, remember it's your theoretical minus your experimental divided by your theoretical times 100. Okay? And this is like an absolute value thing. Okay? So it's never negative. What this does is that it gives us a measure of how close it was to the actual value. So, now, you are going to have to watch your signs because you have a bunch of negatives involved in this. So here's the short version. This is your answer to number 21. This is your answer to number 19. And this is your answer to number 21. So basically, you take 21 minus 19 and divide it by 21. Multiply it by 100. Show me your work. Now, when you get to question 23, okay, let me explain some things I want on 23. You have two different diagrams. Going up the ramp, and then the other one is coming down the ramp. I want you to draw, on the way up, 3 velocity vectors and 3 acceleration vectors. Now, if you want to show that these are changing, show that they are changing. Make them bigger, make them smaller, whatever they want. If you're thinking that these vectors are staying the same size, you make sure that I can look at them and tell these are the same size. You might even use a ruler and go, okay, if you want them to be the same size, always draw them the same size. Then you're going to do the same thing on the way down. You're going to draw 3 different velocity vectors, and you're going to draw 3 acceleration vectors. Again, if you expect me to see that they are changing, draw them so that I can see they are changing. Otherwise, make sure that I can clearly see what you want conveyed. Okay, I'm done. You're on your own. Go be free.